Swayam Prabha. Digital India. Educated India.
Yeah. So let me have your attention. Please take a notebook. Please write. Okay. So you see what we are trying to understand is this business of what exactly the rigid motions are. Okay. And where does this come into the discussion? See, what we have is this. We have this statement that a curve, a space curve, is controlled by its curvature and its torsion. Okay, and of course, to make it accurate, this you have the so-called Frohn-Serre differential equation. Okay, which involves this Frohn-Serre matrix here. Okay, which involves k, which is the k or kappa, which is the curvature, and tau is the torsion. Okay, this is the equation of motion of a particle moving on a point moving on the curve. Okay, and mind you, this is a 3 by 3 matrix. Okay, the moment you see a matrix, you should understand that there's some linear algebra involved. Okay, and so you have to connect to linear algebra. That's one thing. Then the other thing is that there is also this business that if you want to classify curves, then if you take a curve and make a rigid motion of that, you will get the same curve displaced in another direction in space at a different point, at a different region of space. But that doesn't change the curve physically. At every point, its curvature and torsion remains the same. So the point is that, when you want to classify curves up to curvature and torsion, you have to identify curves which are equivalent to one another by application of a rigid motion. So you see this, therefore you get into this business of trying to involve rigid motions, and rigid motions form a group. Okay, that's because every rigid motion can be undone, so it has an inverse, and a composition of rigid motions is also a rigid motion. So you have this composition law. Basically, a group is a structure where you have a composition law. Okay, there is an identity element. Okay, this identity element has this property that any element combined with that element will give back the element you started with. So the identity rigid motion is just the identity map, which means physically don't move. Okay, and you take any rigid motion and combine it with the identity map, you will get back the rigid motion if you compose with the identity map. So the identity map is the identity element for the group. Okay, the group operation is composition of maps. Okay, and composition of maps is associative. Okay, it doesn't matter how you put the brackets. Okay, when you write a finite composition of maps. Okay, so a group is a structure in which a set, a non-empty set with a binary operation, which means a rule of combining two elements. Okay, and this binary operation should be associative, and there should be identity elements, and every element should have an inverse. And all these things are true for rigid motions. You have so if you take the set of rigid motions in 3 space, then that set has identity element as the the identity map, and of course the composition is composition of maps. Composition of rigid motions is again a rigid motion, and composition of maps is associative, so composition of rigid motions is also associative. Okay, and you also have that every rigid motion has an inverse, so every element has an inverse, because the inverse of a rigid motion is the other rigid motion, the unique rigid motion that undoes what the original rigid motion did. Okay, so it's a group. Now the question is, you have to understand this group. You need to write this down mathematically. That's the whole point. And the way to start this whole argument is first to notice that that every rigid motion is actually an isometry. Okay, an isometry is a map that preserves distance. Okay, so every rigid motion is an isometry, and what happens is that rigid motions are almost isometries, except that there is a small bit of difference, and that small bit of difference is what will allow you to connect with linear algebra, okay, and bring in matrices, and it will bring in the orthogonal group. So that's what we are supposed to do. So what I will do is I will just start with the I will just start with the idea, trying to understand what isometries are. Okay, so let me write here, try to understand isometries. Okay, and this is the motivation is because you wanted to try to understand rigid motions which form a group, okay, and a rigid motion is an isometry. Therefore, you try to understand isometries. So let us formally define these things now mathematically. So what is an isometry? It should be a map from space back to itself, and it should preserve distances. So basically, so here's the definition, capital F from Rn to Rn, okay, is called an isometry if it preserves distances, okay. And of course, the distance is the standard Euclidean distance that you have, distance between 2 points given by the usual Cartesian distance formula. So basically, what does that mean? You take in Rn, you take you take 2 points P1, P2, P1 and P2. You take a point P1 in Rn, and then you send it to so it goes to f of P1. Okay, this is another point in Rn. All right, and similarly you have another point P2 which is in Rn, and you are just sending it to f of P2 by this map. Now the point is that the distance between this P1 and P2 should be the same as the distance between their images. That's what distance preserving means. So d Rn P1 P2 should be equal to drn fp1 fp2, and this is the condition. This should hold for all P1 P2 in Rn. Okay, so this is the distance preserving condition. All right, now there is a way of writing this using vector notation. Okay, so let us do the following thing. See, we will follow this business of identifying, so I am drawing 3 space here, but what I have written is for, let us say, any Rn. All right, identifying if you take a point P, let us say in R3 in this case, isometry of R3 will be a map F which will go from R3 to R3. Okay, so a point P will go to a point F of P. All right, now what we can do is you can also write this map in terms of thinking of points as vectors. So think of every point as position vector of that point with respect to the origin. All right, with origin as the initial point. So you can also write this map as P going to F of P can also be written as this vector. Okay, if I call this vector as V, then you have this vector OP vector which is your V vector, and you are sending it to F of V, and F of V will be it will be actually O F of P vector. Okay, so this is the notation. You can, so what I want you to understand is that a point in space is dually being thought of as a point with coordinates, if you want, and also as a position vector of that point relative to the origin. So if you write it like this, you also have a vector notation. You can write F as a map from Rn to Rn, that takes every vector, okay, to another vector. So you can write it like this. They are both the same, okay, but there's one hitch. The hitch is that normally when you start thinking of vectors, Rn is a vector space, because it's an n-dimensional vector space. You can add vectors, you can multiply a vector by a scalar, okay, you have all that. And usually if you have a map between vector spaces, a nice map would be a linear transformation. It would be an R linear map. Okay. But the important point to notice is that an isometry will not necessarily be a linear map, because you see, a linear map has to do three things. It has to take 0 to 0, then it has to preserve addition, okay, and it should preserve scalar multiplication. It should behave well with respect to addition and scalar multiplication. All these three things will not necessarily happen. So the first thing that will fail is, so I will write it here. So I will put this caution symbol, okay, that f need not be linear, okay, from Rn with the additive structure to Rn, again Rn with the additive structure. Even f of 0 need not be 0. Okay, the point is it need not be linear. Okay, so linear map, you need several things. 0 has to go to 0. Okay, then if you call the map as, let us say, G, when is a map G from Rn to Rn linear, then G of 0 must be 0. G of V1 plus V2 should be GV1 plus GV2. Okay, and G of lambda V should be lambda times GV. You should be able to pull the scalars out of the map, the argument of the map. Okay, so in general, when you write the isometry like this in terms of vector notation, you have to be careful that it need not be a linear map. Okay, that means it need not take 0 to 0. But interestingly, what happens is, that is the only hitch. If you correct that hitch, that 0 is not going to 0, then it is literally a linear map. Okay, and that's how you connect isometries to linear maps. And once you can connect it to linear maps, the point is that linear maps is the study of literally in a way study of matrices. So you can connect isometries to matrices. Okay, and once you have this matrix notation, everything becomes very easy, and you can try to manipulate and work with the Frones-Array matrix. Okay, so we want this matrix interpretation of what is going on. All right, so let me make the following statement. So the first thing is, you see, interestingly, you see, rigid motions are going to be distance preserving, so they will be isometries, but isometries need not be rigid motions. Okay, there is a small problem. The problem is, I will tell you what the problem is very easily. You see, you take reflection. A reflection, it is going to be an isometry. It will preserve, for example, if you have a mirror, okay, and you have you put let us say a line segment in front of it, okay, then if you take the image, the image line segment, the original line segment are going to be the same. Okay, so reflection is going to be an isometry always. Okay, but the problem with reflection is that it's not a rigid motion. The reason is because it will mess up the orientation. Rigid motions will preserve orientation. Reflections will reverse the orientation. Therefore, okay, the moral of the story is that you have these reflections which are isometries but not rigid motions. Not all isometries are going to be rigid motions. Not all isometries are going to be rigid motions, and you can expect that rigid motions will, the difference between a rigid motion and an isometry is if it is oriented or if it is not oriented. In the non-oriented case, somewhere a reflection will have to come in. Okay, that's the only difference. Okay, that's how it's going to be. So the first thing I want you to think of is that, you see, just like rigid motions, actually the isometries also form a group. Okay, the composition, the identity map is an isometry, of course. It does nothing. Okay, yeah, the composition of two isometries is also an isometry, remember that. That's because, you see, a composition of two maps which preserve distance will also preserve the distance. Okay, therefore composition of isometries will be also an isometry. What is not trivial is, an isometry will have an inverse isometry. This is something that you can think of geometrically. Okay, but an isometry will always have an inverse. Okay. Now, here is where you need a little bit of math and the connection to linear algebra. See, normally if you want inverse of a map, first of all, it should be bijective. Unless a map is bijective, I cannot define its inverse. All right. So it's not even clear that an isometry is, bijective. So if you look at it, what is immediately clear is an isometry is always injective. Okay, that's because of the distance preserving property. So let me write the following thing. So fact is you have a question. That's right. That's the decomposition that I'm going to do. Essentially, I'm going to say that every isometry is up to a translation a linear isometry, and a linear isometry is going to be given by a member of the orthogonal group. That's the decomposition I want. No, see, if it is an isometry, it has to necessarily be linear. If you use quadratic or some other functions, some scaling will start coming in. Because those functions, you see, what will happen is their derivatives will not be constant. And the derivative of the function is going to be the Jacobian of the transformation. It will be a scaling factor for the measure element. So what will happen is you cannot help it. If you take higher nonlinear things, the Jacobian will not be a constant. Okay, actually the Jacobian should be 1. It will be a non-constant function, in fact. Then you will never get an isometry. Isometry is necessarily linear up to a translation, that's all. Okay, so you cannot use other functions. Okay? It's a very strong condition. Okay, so here is the fact. The fact is, the first thing is any isometry is 1, 1, which means it is injective. What is the proof for that? You see, f is so basically if you take an isometry like this, suppose I write it in this notation, this point notation. So f is from Rn to Rn, it's an isometry. How do I show it's 1 to 1? If f from Rn, so for if f from Rn to Rn is an isometry, and how do you verify a map is injective? If the images of two elements are the same, then you have to say those two elements are the same. But that's very trivial to verify. And f of p1 is equal to f of p2. Okay. Then what happens? You see, the distance in Rn between p1 and p2 is the same as the distance in Rn from fp1 to fp2, because this is the isometry property. This is the distance preserving property. But you see, fp1 is equal to fp2, therefore this is 0. The right side is 0. And therefore the distance between p1 and p2 is 0, which will force that p1 equal to p2. So this implies, p1 is equal to p2. So if fp1 is equal to fp2, then p1 equal to p2. So that is the proof that, any isometry is 1 to 1. What is not trivial is that any isometry is also surjective. It is onto. Okay, that is what is not trivial. And to understand that, what you have to do is you have to connect the isometry to a linear isometry and use linear algebra. You have to go to linear algebra and use the so-called rank nullity theorem. Okay, so here is where the linear algebra comes in. So here is another fact to be seen. Any isometry is also surjective, is also onto. Onto is the same as surjective. Okay, and therefore, the advantage of this is that all isometries will become bijective. The inverse of isometries will also be isometries, and the isometries themselves will form a group. Okay, so that's what is going to happen. All right. So how does one go about this? You have to connect with linear algebra. So here is a nice. Let me call this as lemma. Okay, very nice lemma. So I told you, you start with an isometry. The first problem in connecting it with linear algebra is that it's not a linear map necessarily, because it need not take 0 to 0. So what you do is, you try to rectify that. So what you do is, you take this map, it will take 0 to something, then you undo that by translating by negative of the image of 0. The resultant will be an isometry that will take 0 to 0. Okay. then what will happen? Here is the magic. If you have an isometry that takes 0 to 0, then it is necessarily a linear map. Okay, so that is a beautiful thing. Just if you fix this issue that 0 is going to 0, is not going to 0. Okay, if you can fix that, then the isometry will become a linear map. So the difference between isometry and a linear map is just a translation. Okay, that is the whole point, right? Mind you, for a map to be linear, you need 3 conditions. 0 has to go to 0, addition has to be preserved, scalar multiplication has to be preserved. There are 3 conditions. Okay, but and the problem with an isometry is even the first condition is not satisfied. 0 does not necessarily go to 0. The amazing thing is you fix this first condition, make 0 go to 0. Then the resulting map will be an isometry that fixes 0. That will automatically satisfy the other 2 conditions. And this is because of the distance preserving property. Okay, and essentially because of the fact that angles are preserved. Okay, so let me explain this. So let me write this down. So what I'm going to write is let f from Rn to Rn be an isometry. Okay, consider the map G from Rn to Rn, okay, defined by, so G of V, okay, is going to be, you take f of V, okay, and then what you do is that f need not take 0 to 0, okay, but I want G to take 0 to 0, so what I'll do is I'll subtract f of 0. Okay, this is for all V in Rn. You define the map like this. Then you see what you can see immediately. So let me write the conclusion. Then G is a linear isometry of Rn. Okay, right? And let me look at this. The first thing is, you see, G is an isometry is very, very clear. Okay, G is an isometry is fine, because you see what is G of P1 minus G of P1 minus G of P2. So I think, let me write it like this. You have to show the distance between GP1 and GP2, okay, is the same as the distance between P1 and P2. But the distance between GP1 and GP2, you see, so I want you to understand that, so how do I say this? What do I want to say? Yeah, so there is something here I wanted to, so let me draw a picture. So I have, at least this picture works in, I can only draw R3, so but the same kind of picture you can imagine in any Rn. So you have this P1 and P2, okay. There is this, so there is this vector which is V1, okay. Then there is this vector which is V2, all right. And then you have, see, I want you to understand what is the meaning of this distance between P1 and P2. You can see it is it's also the distance, the length of the vector P1, P2, okay. And that is the same as, position vector of P2 minus position vector of P1, okay. So this is just by ordinary vector addition. So I just want a little bit of that interpretation here. So you see, this is your picture. What you can see is that the distance in Rn between P1 and P2 is the same as the norm of let me say V2 minus V1, okay, from the picture. And so I have to compute this guy, the distance in Rn from GP1 to GP2, okay, will be therefore norm of GV2 minus GV1, okay. So you see, what is happening is that there is this map G, okay. This map G, what is it going to do? It is going to map uh, you know, P1 is going to go to GP1, okay, P2 is going to go to GP2, okay, and this vector will be the position vector of G of P1, and that is going to be just G of V1, okay, and this vector is going to be G of V2, okay, and this vector will therefore be the position vector of GP2 minus position vector of GP1, right? And notice that it is important that 0 goes to 0 under G. Okay, so this is how this picture looks like. All right, so if you calculate the distance between GP1 and GP2, it is going to be this norm, and you just plug in this, okay, and you get this. But this is, this is so I should say this is the same as distance in Rn of f of P1 and f of P2, okay, but then f is an isometry, so this is the same as distance in Rn between P1 and P2, and that is the end of the proof. Okay, is that clear? Right. So the moral of the story is that this G is an isometry, right? See, another way of understanding this is that if you want, if this looks kind of too mathematically elaborate with a lot of notation, there is an easier way to look at this. You also have this business of the idea of a translation. Okay, so if V naught is a, let us say, a vector in Rn, okay, I can define this T V naught, translation by V naught. This is a map from Rn to Rn, which is just translation. You take any V and send it to V plus V naught. Okay, this is a translation. This is called translation by V naught. Okay, now the fact is that you see this translation is an isometry, of course. Why? Because you see, if you calculate T V naught, suppose I take 2 points, let us say P1 and P2, and calculate the distance between their images under the translation by V naught. Okay, what will I get? This if P1 is represented by V1, then I will get dRn by definition. This is going to be T V naught of V1 vector. So you see, there is this duality of trying to identify every point with its position vector. Okay, and this is something that you should get used to. So T V naught of P1 can also be written as T V naught of V1, where V1 is a position vector of P1 with respect to the origin. Okay, and this is going to be T V naught of P2. So this is going to be T V naught of V2. Okay, all right, and then this is going to be by if you write it in vector notation, this is just the norm of the difference of the two vectors. So it's going to be T V naught V1 minus T V naught V2. Okay, but this is just addition of V naught, so this is going to be V1 plus V naught, and minus I will get V2 plus V naught. Okay, and this is this V naught is going to cancel out, and then what I'm going to get is norm of V1 minus V2. Okay, and this is by definition the distance in Rn between P1 and P2. Okay, so the distance in Rn between the translates is the same as the distance between the original points. Okay, this is something that, I mean, if you write it down, it looks messy with some notation. Okay, translation is not going to affect the distances. Translation is an isometry. Okay, and basically what I am doing here is, if you give me any isometry, when I define this G is GV is FV minus FV naught, what you are doing is, you are applying F to V, then this minus F of 0, this minus F0 is translation by minus of that vector which f of 0 is. So it is actually applying f first and then applying a translation. So it's a composition of f and a translation. Okay, but f is an isometry, translation is also an isometry, and a composition of isometries is an isometry. Therefore, G is an isometry. So that is another way to see it. Okay, so notice that G of V is equal to f of V minus f of 0 means, G of V is actually translation by minus f of 0, okay, acting on f of V. Okay, that is what it means, is that the G is composition of this translation with f. This is what it is if you write it as composition, and this f is given to be an isometry. Okay, and translation is also an isometry, and a composition of isometries is an isometry. Therefore, this implies that G is an isometry. Okay, therefore, if you start with an isometry which does not take 0 to 0, if you do this, if you take away from that isometry the image of 0, which amounts to applying this transformation that moves the image of 0 back to 0, then the composition is going to be linear. Okay, the composition will be an isometry. In fact, the claim is that this is actually linear. Okay, so the claim is G is linear. So G is a linear map. Okay, now how will you show that G is linear? So for that, what one has to understand is that, so let me say a few things. You see, a map which preserves distances will also preserve angles. Okay, so it will preserve dot products because the angles are determined by the dot products. Okay, so what I am saying is the following. So you see, if you have, so let me make the following statement. F is from Rn to Rn, and let us say it's just an isometry. Okay, that means it preserves distances. Then I want to say that it also preserves angles. Okay, so what do I mean by that? So you see, suppose I take, so of course I am drawing the picture for R3. Okay, but you can imagine the same kind of abstract picture for Rn. Okay, all I am going to do is just take, let us take 3 points, let us say. Okay, and call them as, if you want, I'll call them as A, B, and C. Okay, and now you see, I get this triangle ABC. Okay, and you apply F to it. What you'll get is, you'll get another triangle. Okay, again I'll get a triangle somewhere here. Okay, let us say. Okay, the fact that F is an isometry will tell you that you are going to get only a congruent triangle. Okay, because you see, this distance between A and B is going to be, so I have to, so when I apply F, I should label these as FA, FB, and FC. Okay, so this triangle ABC will give you this new triangle. See, the distance between A and B, that will be the same as the distance between FA and FB, because F is an isometry. The distance between B and C will be the same as the distance between FB and FC, again because F is an isometry. And the distance between A and C will be the same as the distance between FA and FC because F is an isometry, right? You have a question? No. So I am just trying to tell you that isometries will preserve angles, but in general, if only angles are preserved, it's going to be a similarity. It's not going to be a congruence. Isometries will give rise to congruences, but even similarities will preserve angles. Scalings will also preserve angles. See, congruence, for example, when you study plane geometry, congruence of triangles is stronger than, similarity of triangles. Certainly congruence is a similarity. Okay, so in that sense I am saying. So I'm just trying to say that I'm just making some observations. I'm saying that an isometry will always preserve angles. The reason why it will preserve angles is because it preserves distances. And actually the sides of a triangle also determine the angles of the triangle. That's the whole point. So basically you see, I have this isometry f from, in this case I have drawn it from R3 to R3. So if you want, forget the axis and think that this triangle is in n space also, it really doesn't matter. You have this triangle ABC, then you have the image points FA, FB and FC, they also form a triangle. These two triangles are congruent. Okay, that's because F is isometry. But also the angles therefore will be the same. So in fact, what, for example, you know, what is this angle? This angle, you know this, you have, for example, you have the cosine rule, right? So if you call this a small a and small b and small c, okay, then you know a squared is equal to b squared plus c squared minus 2bc cos angle a, right? You have the cosine rule. So, but you see these lengths A, B and C are going to be preserved. So, in this triangle also you are going to get A squared is equal to B squared plus C squared minus 2BC cos, here I will have angle FA. So, you see the angles will be the same. So, if you want to use plane geometry, you can think of it like this, okay? But there is a way of again writing it using vectors. So, how do you write it using vectors? Here you see this, how do you get an angle? The cosine of the angle is connected to the dot product. So basically you have AB vector dot AC vector is equal to norm AB norm AC into cosine of angle A, right? And what I want to say is that the on that is on this side you will get this. On the other side, what are you going to get? You are going to get so I have to write it as FA FB vector dot FA FC vector is equal to norm. So I will put norm here. Norm FA FB norm FAFC into cosine of angle of angle FA. Okay, and the point here is that it is this dot product that is being preserved by the isometry. Okay, and how do you check that the dot product is being preserved by the isometry? I will make an observation first. Okay, so F isometry implies that f of v1 minus f of v2 norm is equal to norm v1 minus v2. Okay, this is the definition of an isometry. Now see, the idea is that I am trying to say that the dot product is preserved. Okay, I am trying to say that the dot product is preserved, and the trick is always to be able to connect the isometry property, which is a distance property. It's a norm preserving property with the dot product. And what is the connection between the norm and the dot product? The norm of a vector squared is the dot product of the vector with itself. V dot V is norm V squared. Okay, that's how you connect the dot product with the norm. So that is what we'll have to do. I want to take this property, which is a distance preserving property. It's a norm preserving property. It has got to do with the norm, but I want to say that it is also going to preserve angles. So essentially I want to say it preserves dot products. So what I have to do is I have to move from the norm to the dot product. And the way of moving from the norm to the dot product is that the dot product of a vector with itself is the square of the norm. So basically what you do is that you take square on both sides. So you norm fv1 minus fv2 squared will be norm v1 minus v2 squared. All right, and then you see, use the fact that the norm squared is vector dotted with itself. So what will happen is that this will be fv1 minus fv2 dotted with itself. okay, is equal to V1 minus V2 dotted with itself, okay. And then, so let me draw a picture here. So I need a picture. Yeah, so what is bothering me is the fact that 0 is not going to 0. That's what is troubling me. Here what is going to happen is, you see, you have to account for f of 0 here, okay. See, the problem is this f is an isometry, 0 is not going to 0. So what will happen is that, you see, this is the vector which will be f of this v1 vector, okay, as a vector, okay, but it's not based at 0, right? And this is the vector which is f of v2 vector, okay. And actually this angle will be actually this angle, okay. You have to be careful about moving the origin, okay. If you don't keep, and see, the way to do that is, I have to I have to write fv1 minus f0 minus fv2 minus f0. I have to bring in 0 everywhere, all right. And then if you write out this dot product, you will see that if you expand it, you will see that, f will preserve the dot products, okay. So this has to be written down. So I'll do this again. For the moment, let us keep it that at least it's clear that you take an isometry, it need not take 0 to 0. So you undo that by following it up by another isometry that brings the image of 0 back to 0. Then this is the new map G. So finally you will get an isometry that takes 0 to 0. Then this claim is that this is a linear map. And in fact, it is actually a linear isomorphism. Okay, that is the claim. So it's given by an invertible matrix. Okay, and finally, what is going to happen is that this invertible matrix is actually going to be an orthogonal matrix. Okay, so that is what is finally going to happen. So we will see that. We will see that in the next lecture. Okay, so we will continue.